Good afternoon, everybody. Welcome to week number 4. It's right here. So today we are going to finish talking about the sun, and we will start with our next topic, which is star formation. So a lot of people are still joining, but let me just tell you the main announcement is that you have a midterm next week on Monday. The midterm is going to be timed, so you only have 1 hour to finish it. I have accommodation letters for several students, so if you have submitted your paperwork, you don't have to worry about anything. You will get more time automatically. Otherwise, if you haven't done so, you need to submit your paperwork. For the midterm will be on iLearn, and I will send you this week an announcement email telling you the details about how to access it. What I usually like to do is do a little practice, just some silly questions exam, so that you know how to go to iLearn. You can make sure that you know how, where to click, how to start. And so it's just a practice thing. It's not real questions. So that you can get practice if you have never taken a test on iLearn, which I'm sure there's many of you who haven't. So it'll be obvious. You will get to iLearn. There will be a button that says exams, and you'll be able to click on it, and then you will have access to the test. I will be on Zoom the entire time while you're taking the test on this link for the lecture. So if at any time during the test you have questions, you would like me to clarify anything, you can log on to Zoom and you can use the chat window so you can ask me the questions. That's probably the easiest way to contact me. The exam will cover lectures 1 through 9, so all the way to Friday, and homeworks 1 through 3, which homework 3, if you notice, if you downloaded it already, it has a couple of questions that I will cover today in lecture. So the midterm does cover a little bit of today's lecture. Yeah, so just to clarify a question, you do not need to be on Zoom while you're taking the test. You can go on Zoom. Some people like to do that. They like to, if they have the bandwidth with their internet, they connect to Zoom, and then at the same time they're taking the test. And that way Zoom is available in case they need to ask anything. But you don't have to. That's completely optional. You will not be proctored. I am trusting you that you will not cheat. The only way to cheat is to talk to other people, whether it's on, on a forum or texting or emailing. All of those are not permitted. You cannot communicate with anyone other than myself or your TAs, and anything else is fine. You can do anything else for the test. The midterm is multiple choice. It will be about 30 questions. And there's 4 different types of questions. The usual multiple choice that we do with the polls. Also multiple option, that's when more than one question is correct. And then so those are 2. And then there's true or false. That's you're familiar with that. And then the 4th type, which I don't use very much, but I do like to use it sometimes, is when you have to order things. Like, so I will say, please arrange the following in order of size, for example. And then I will give you several things. So size could be a planetesimal, a terrestrial planet, a Jovian planet, a solar system, a galaxy, right? So you know that all of those are different sizes, and then they will be all shuffled, and then you'll have to put them in order. And I know students sometimes struggle with that, so just make sure you think about it carefully and then go on and arrange it. Okay, will partial credit be given for multiple answer type questions? Yes, and in some cases, if you choose the wrong question, actually in all cases, if you choose the wrong question, you will be deducted some credit. The reason why this has to be done is because otherwise everyone would just choose all the answers, right? And then you would automatically get it right. So we have to deduct points if you choose the wrong one. What time will be the test? At 4. And the paperwork to submit. Okay, so sorry, I didn't mean to confuse. Some of you have accommodations through the SDRC. So if this is you, if you have accommodations for tests, you need to submit the usual paperwork that you submit, so that you can be given accommodations, right? Sometimes they provide a place for you to take the test. Sometimes it requires that I give you a little more time. It varies from person to person, but if you are not familiar with this, it means you don't use it, so it doesn't apply to you. The link to the exam will be on iLearn. So this week I will send you an email with detailed instructions on how to access it. And I will also give you a practice mock-up test, right? It won't be a real test. It'll be just a few questions, a couple of questions, just to give you practice on how to get to the test and how to take it. And one final thing. One final thing. Internet can be an issue, right? I mean, you can have an internet glitch. You can sometimes the system is silly and it kicks you out or something like that. So to accommodate for this, I am going to be allowing 2 tries for the test. So let's say you're taking the test, you lose the internet and it didn't save. It should save, right? Usually if it kicks you out, it should save where you were. And when you go back, you should be able to find the test where you were and pick up from where you left off. But sometimes it doesn't, right? Sometimes it crashes. So to make sure that everyone gets a fair chance, if that happens to you, you have a second try. You're able to take it again. I mean, to start over again. Now, I can't control who takes the second test or not, or the second chance. So if you finish the test in 15 minutes and you think you can try it again and you think you can do better, you're welcome to do it. I doubt that you will have time to do it again, but if you have plenty of time left and you're like, oh, there was this one question, I knew it was going to be wrong, and then you can try it again. The test will not tell you which ones you got right and which ones you got wrong. It will only give you a total score at the end. Okay. Yes. So okay, so somebody was asking me about the internet, and yes, the midterm is open book, open notes, open anything. What else? Okay. If you take both tests, I will take the second try. So you have to be careful with that. Okay. Very good. So if you have more questions, you're welcome to come to office hours or email me or ask me next class. But I'm going to move on now from the announcements. Again, look for your email sometime this week, maybe probably by Wednesday. I will send you an email with instructions and with a demo test, right? Like a practice test. That is, it's just a demo. It's just a few questions and it doesn't count and it's optional. And the only purpose is to make sure that you know how to access a test on iLearn. All right, so let us move on. And last time I ended with this slide. And the last slide where I was telling you that the sun goes through this cycle where sometimes it shows a lot more activity and which people have been keeping track of by looking at how many sunspots. So if you remember, sunspots were those regions in the photosphere or in the surface of the sun where the magnetic fields get so tangled that they sort of poke through the photosphere, and then convection cannot happen. So then it starts to get a little cooler, and because it is cooler, it gets darker. It looks darker. So these sunspots, since 1700s, people have been looking at the sun and drawing pictures of the sun and counting the number of sunspots that they get on any given day. And it turns out, if you plot the number of sunspots that people have seen as a function of time, from 1700 to today, you will see that there is this periodic behavior where sometimes you get a lot more sunspots and then you get less. And the times when you get the highest number of sunspots correspond also when there is the great majority of activity on the sun with the solar prominences, and also something we will learn today, solar flares and solar coronal mass ejections, which we'll talk about in a minute. So again, this corresponds to solar maximum when you get the most number of sunspots, and solar minimum when you get the least sunspots on the surface of the sun. And what scientists have been able to figure out is that this periodic behavior corresponds to a reversal in the polarity of the sun. So last time I told you that the sun was like a magnet, and I don't know if this will show at all, probably not, but this is a cool cube. Yeah, you can't really see it. Let's see. Nope, you can't see it. Anyways, it is a cool glass cube that has an etched sun with a bunch of magnetic field lines. And what I wanted to show is the magnetic field going from north to south pole. After 11 years, it gets pretty tangled and it begins to switch little by little, like some of patches that were north become south, some of the patches that were south become north, and then after a while it reverses totally, so that when you measure the magnetic field, all of what was the north is in the south and all of what was the south is in the north. So it flips around. And then again, 11 years later, roughly, right? Sometimes it is 9 years, sometimes it's 10, sometimes it's 13, but around 11 years, it reverses again. And so what we think that happens is that, well, actually nobody quite understands why or how this happens, but it gets pretty tangled to the point that it just sort of reverses itself. In the history of Earth, this has actually happened too. Earth, you have a compass and you look for the north magnetic pole by seeing where your magnetized needle in your compass, points toward north. On Earth, it has happened not every 11 years. It has happened, every, I actually don't know how often, but maybe thousands of years, maybe millions of years. But it has reversed too. And we don't understand why it happens. But it happens. Every 11 years, roughly, the sun reverses its magnetic field. And then it sort of starts over, the cycle again. So you might wonder, where are we now? And I was going to show this picture on Friday. I looked up, if you guys go to this website here, you can actually see what the sun looks like right now. And today it looks different. I looked it up before class and it just looks a little different. This is what you would be able to see with your eyes. It only has one sunspot that you can see over here on the right. The picture on the left shows you the magnetic fields. They measure the magnetic fields, and you can see white and dark spots are places where the magnetic fields are sort of peeking or poking through the surface. And one is North Pole, the other one is South Pole, you know, of the magnetic field line. I don't know which one is which one, but you can see how they come in pairs. There's some darks and some lights, and same here. And there's a pretty big one here, which corresponds to what you would see with your eyes, which is a sunspot over here. And then if you see it in a different wavelength of light, which we'll learn about next class, but if you see it with a different type of light, then you can see the hot gas or the cooler gas that is going around, and maybe you can see that there is a prominence here that is connected to the sunspot. So this doesn't look like a lot of sunspots, so you can probably guess that we are not at a solar maximum. But where are we on the sunspot cycle? Well, here it is. In around 2014, we had a maximum, which was actually a very wimpy maximum. It wasn't very spectacular at all. And then we went into minimum, and here we are at 2021. We're going back up, and so it's pretty low, and we expect the maximum to be around 2026 or so. So you have to wait until then to see a lot more activity in the sun. But again, you can go to this website anytime, and then you can see the pictures from today. These are pictures taken by NASA satellites that are constantly looking at the sun. Just to clarify, prominence is the glowing gas. Yeah, prominence, I don't have the slide anymore, but it was when gas climbs up on a magnetic field line, you know, through a loop. So you know, the gas goes up and then down, and it looks like an arch or a loop above the surface of the sun. Are there more sunspots for solar maxima? The question is it maxima or minima? So again, going back to this slide, this is a solar maximum when you get a lot more sunspots. This is a solar minimum when you get much fewer. Is there an effect on Earth when the sun reverses its poles? No. The only effect is sort of secondary, and it is in the fact that after it reverses the poles, we go into a minimum, and the minimum is actually better for Earth, but we'll get to that. And so north becomes south and south becomes north. Yes, that's right. Okay, I think I got to all the questions. So yeah, we were here. So that's where we are right now. Okay, let me tell you about two more things on the sun, on the surface of the sun, violent phenomena that are connected to the magnetic fields. And one of them is solar flares. So solar flares are much more violent, right? The prominences, you know, the loops that I was talking about, prominences are not exactly violent. They happen little by little. They're huge, they're kind of scary, but they're not violent. They happen slowly. Solar flares, on the other hand, occur when the magnetic field lines are so twisted that they start to get really, really tangled. And then sometimes the magnetic field sort of touches, if you will, or they, yeah, let's put it that way. It touches itself and then it kind of snaps. So if you think about it with an analogy of a rubber band, like you twist it, and it keeps getting tangled and kinky until you twist it so much that it snaps. So it's something kind of like that. The magnetic field line doesn't snap, it doesn't break, but it's similar in that it suddenly releases a lot of energy. And as it releases the energy, this results into a brief eruption of hot gas. So it sends bursts of hot gas, charged particles, you know, this plasma thing that I've been talking about, into space. X-rays, that just comes from the fact that it's very hot. And so it goes off into space, and I have the movie here of an actual, I mean, this is an actual movie of the sun. It's not made up. They're usually connected to groups of sunspots, just like I showed you in that other slide. So anyways, so this is a solar flare. They're huge, right? They're gigantic. So I showed you a comparison last time of prominence compared to Earth. Look at the comparison of a solar flare to the approximate size of Earth. So really, really huge. Thankfully, really, really far away too. How is it that they're powerful enough to leave the sun's gravity? Yeah, I mean, they're just very fast. And that's why they're able to leave this, the sun's gravity. All right, so next thing is coronal mass ejection. So CME is for short. Every time you hear the word CME, it refers to that. Coronal comes from the fact that it's the outer layers of the sun. Mass, because there's a lot of mass that is ejected. So a coronal mass ejection is a much larger eruption, much, much larger, right? So here you see the size of the sun would be this white circle. And what these telescopes that are in space, what they do is they have to put a circle, a disk in front of the sun to block it, right? Because if you take a picture of the sun is so bright that all you see is the sun itself. But if you want to see the stuff around it, which is bright but not nearly as bright, it's, you know, it's kind of like when you want to see far away and the sun is right in your eyes, you kind of put your hand, you know, to block the sun so that you can see the stuff around, right? In the same way, they put a disk in front of the sun, you know, kind of like your hand covering your eyes, and then they're able to see the stuff around it. If you're interested, this is called a coronagraph, but you don't need to know that. So once they cover the sun, they can see this gigantic coronal mass ejections, which, I mean, look at this, look at the size of this compared to the size of the sun. So it's even bigger than the sun itself. If you were to put, you know, the Earth to scale here, it would be a tiny little dot. This is billions of hot gas, billions of tons of hot gas that is blasted into space at hundreds of miles per second. Here's another picture, an even bigger one. And there they put a picture of the sun in the middle so that you could see more or less what it looks like at that particular moment. Good, so I have several questions. I'll get to them in a second. So here's another picture, glorious picture, which I think I have it right behind me too. So this is what we call space weather. So whenever you hear the space weather, it refers specifically to the behavior of the sun, right? So when the sun has a lot of activity, like in this video, you see a storm, because there's all these spikes that you see on the sides. That's just the solar wind coming, you know, the regular, and then you see these explosions or these ejections. Those are the CMEs, and you see, you know, some flares here and there. What's the difference between a flare and a coronal mass ejection? Mostly size. So they are similar, they're produced in a similar way. A flare is a little bit smaller. A coronal mass ejection, I like to say that it is a flare on steroids, right? It's just a much, much bigger thing. So very good. Now, a lot of you are asking the question, which is great, right? What happens to the planets that are close to the sun? And the answer is similar to what happens to Earth. So let's focus on Earth. Let me get to your questions first, because okay, I guess you guys are all anticipating. All of your questions are very similar, which is what happens to the planets, right? So first of all, when you look at this, a lot of the coronal mass ejections that we see are going in a different direction, right? Thankfully, none of these that you're seeing here is coming toward us. But chances are, every once in a while, one of these coronal mass ejections come toward us or toward any of the other planets. So what happens when a CME heads straight toward Earth, right? Sometimes it'll happen. And this is just an animation where you get the surface of the sun and there's activity and boom, there's a coronal mass ejection and it just happens to go straight into Earth. So as it reaches Earth, here's the really good news. We ourselves have a shield. So remember, coronal mass ejections are made of plasma. The stuff that is coming, the mass that is coming toward us is plasma, which is charged particles, right? It's ions. So charged particles, if you remember, can interact with magnetic fields. And just in the same way that the plasma would climb up through the loops on the solar surface, in the same way they can interact with the magnet that is protecting us. So the Earth has this magnetic field around it. It's actually called a magnetosphere. So magnetosphere is the region around the planet that is occupied by its magnetic field. Not all planets have magnetospheres. Jupiter has a really big one. We have a magnetosphere. Other planets have magnetosphere. The moon doesn't have one. So some of them don't have this protection. Some Mercury doesn't have a magnetosphere. So one of you was asking about poor Mercury. It's like, oh, how's Mercury doing? Every time that this stuff comes toward Mercury, it doesn't get protected by the magnetic field. This magnetosphere is fantastic. It actually, as you saw, the plasma it's like if a river found a rock. You know how in a river is coming down, the water is flowing, and there's a rock, and then the water sort of forms this shock, which is what is pictured here. And then it goes on the sides. So most of the coronal mass ejection actually goes around those, and that is fantastic, and it's amazing. It's really good. However, remember that we have a tilt in our planet, in our rotation axis and our magnetic poles. So the magnetic field lines are coming out from the top and the bottom. So that means we have some weak spots on either side of the poles. And as the solar wind or the coronal mass ejection or anything coming from the sun comes to us, most of it is going to go above and below and on the sides, right? It's going to bypass us. But if you have enough stuff coming our way, if you have a coronal mass ejection that is really big, then some of the particles, or maybe a lot of the particles, are going to leak in through these more vulnerable spots on the north and on the south, and it might make its way to us, to our atmosphere and to us. What happens then? What happens if some of these charged particles make it to our atmosphere? There's good and there's bad. Let me start with the good. The good is when we get this beautiful fireworks or this beautiful show of lights, which we call either the northern lights, the southern lights, or the aurora borealis or aurora australis. I have a really hard time saying these words, but you can read them. So this is what we call the aurora, and it's on my bucket list. It is definitely something I want to do sometime before I die, to go to the north part of the planet, or maybe the south, and to get to see this. So when does this happen? When the magnetosphere is overloaded by the flow of charged particles from the sun, they can cascade down toward the atmosphere and they produce this aurora. What you see, which looks beautiful and colorful, what you see is actually those ions, those plasma particles that are interacting with the elements in our atmosphere. Our atmosphere has a lot of nitrogen and oxygen and some other elements. So as they interact with those elements, they produce some light, light of different colors. Which colors? It depends on the elements. So for example, oxygen produces some really beautiful green light. And so that's what you see. You see particles that are coming straight from the sun that are dancing around with our atmosphere. And I have some pictures because, again, I absolutely love this. And so, you know, I love looking at pictures of the aurora. And I actually follow on Twitter, I follow this guy who goes around the world taking pictures of aurora because it's so beautiful. This is a picture that this guy took. It's an actual photograph, right? And on the right, you see the aurora. On the left, you see our galaxy, the Milky Way, which we'll talk about in a couple of weeks. Here's the aurora over Iceland. And here's the aurora taken from space. So astronauts can actually see it. And here you can see very clearly how it is those particles that are above the surface of Earth just interacting with our atmosphere. Here's another picture. And you can see very clearly here, this is the South Pole. You can see how it is right around, you know, where all those magnetic field lines are coming out. That's where you get a lot of this aurora. I have some questions. Let me see. Do I know which elements create each color? Yes, for sure. I mean, in a picture like this, let me see. Yeah, for example, this one. The yellower ones are sodium, the redder are hydrogen, some of the blue is hydrogen too, and the green is very much, I said it before, oxygen. Some of the red is also nitrogen. And if you're more interested, like I can tell you how I know, but not in class. So you're welcome to come to my office hours. Let's see. So yeah, I'm getting the question by several of you. When during the year, when do you see them? Well, there's a few things. It has to be dark, right? You can't see this during the day. I mean, you could if it was really strong, but mostly you can see it during the night. And if you guys know, if you're familiar with this, if you go to Alaska, for example, during the summer, it never gets dark. It's like daytime all day. So the summer is not great, not because there aren't any aurora, but because it's more difficult to see it. So it happens anytime that we get enough solar wind coming our way or a coronal mass ejection coming our way. So it can happen any time of the year, but you have better chances of seeing it when it actually gets dark during the night. Mostly, you will see this in the northern and southern hemisphere. I mean, not just hemisphere, but let me go back to this. So again, you can see how you will be much more likely to see it on the sort of the northern regions. So, you know, northern Canada or Canada, just Canada, Alaska, Iceland, Greenland, Norway, you know, sort of northern Russia, you know, all of that is a much better place to see it. And then in the south, you have to be going pretty far south, you know, like the tip of Argentina, Chile, southern Australia, and I don't know, maybe southern Africa. India, not so much, because it doesn't go south enough. So yeah, it's you kind of have to travel unless we have a really big coronal mass ejection, which I'm going to get to it. So I'll read some of your comments while I show a video in a few slides. Let me. So anyways, I leave you with what do you call this? A link in case you want to see some time lapses of aurora. And also, that's just a nice video that follows the life of a sunspot for 2 weeks. But let me get to the next thing, right? So that was the good. I told you there was good and there was bad. So the good is you get this beautiful display of lights called the aurora. The bad is these are charged particles, which while they don't really hurt you very much, you know, well, they might hurt you a little, but they mostly interact with electronics. So charged particles, you throw them at your computer, that's bad for your computer, for microchips. So what solar storms can damage is microchips from satellites, right? Because satellites are above this, or not above, but they're higher up within this magnetosphere. So they are less protected and they are more vulnerable to solar storms. Shortwave radio transmissions, you know, including your cell phone when you talk, can be affected also by these solar storms. And here's the worst one probably, which is power grids can be disrupted. If you get enough of these charged particles going into a power grid and it gets overloaded, it can take it down. And in fact, this has happened before. So in 2003, a solar storm caused a power outage. I can't remember exactly where it happened, but somewhere in the US, there was a big power outage. And then it affected half of the NASA satellites. So you can see in this video, like all of a sudden, the satellites that were looking at the sun, for example, all of a sudden they get all this noise, all this static. Those are the charged particles that are coming from the sun. And some of them were actually damaged. I mean, some of them were just like blinded for a little while and then they were fine, but some of them were actually damaged. And this is not that long ago, right? Like,
oh, shoot. Thank you. Hold on, sorry. Yes, please.
Okay. Amari, yeah, there you go. So like I said, this is 2003. I think the majority of you were alive by then, so it's not that long ago. Longer ago, oh, somebody told me the power outage was in Texas. Thank you. So longer ago, longer than that, but again, still within your parents' lifetime, 1989, there was another CME, and the entire province of Quebec in Canada, so it's this entire big dark spot in the map, in 1989, suffered a 12-hour power outage due to a CME. So that's bad. Can you imagine like being 12 hours without power? That can be pretty bad. And again, this is because the power grid gets overwhelmed and then it can take it down. So has there been anything bigger than that, right? I mean, these are bad, but not terrible. In 1859, and by the way, please don't memorize any of this. This is just, don't memorize the years is what I'm trying to say. So in 1859, there was a gigantic CME, the biggest one that we have on record, and it hit Earth. So the main effects back then were disrupted telegraphs, because that was like their main source of communication at long distances. And then this is so a bad one and a good one, right? It created auroras that were visible down to the equator. So all the way, you know, from Mexico, from Panama, you could see them because the magnetosphere got so overwhelmed that the auroras went all the way down. So basically from anywhere in the world, you could see the auroras, which is amazing. But here's the big difference between 1859 and today. They didn't have electronics, right? They didn't rely on electricity, whereas we do. So if there was a superstorm that was as big as the one in 1859, it could disrupt most of the US power grid, and US and the world, right? Not just the US. And they estimate that it could be disrupted for up to 3 months, which is a lot more than 12 hours. So I have a video from a documentary. So I have a clip that I'm going to play now while I read your questions. So.
Scientists have long suspected that a super CME, when it does happen, could be disastrous. The last such event to target the Earth happened in 1859, disrupting telegraph service and creating auroras visible down to the equator. An event like that today would mean power outages on a scale we've never experienced. Much of the US power grid could be down for 3 months, and perhaps much longer.
If we lost electricity for 3 months or more, the effects, especially on a country like ours that depends on electricity so much, would be devastating. You can only imagine what it would be like. People would freak out, really. I mean, we wouldn't have refrigeration, we wouldn't have lights.
Without the artificial eclipses in our solar satellites, we would have no idea that such a threat even existed. According to recent estimates, full recovery could take 4 to 10 years. Millions of people could die due to shortages of food, clean water, and pharmaceuticals. Projected damage may be as much as $1 to $2 trillion, comparable to 20 Hurricane Katrinas. A super CME struck the Earth 150 years ago, but scientists disagree on when the next one could come.
The likelihood of that happening in our lifetime is probably not that good, but we just don't know. We don't have enough data.
The most powerful coronal mass ejections that could cause widespread damage over all of Earth probably occur only about once every millennium or so. Nevertheless, having a huge calamity every few thousand years is really a big deal.
All right, so some of your questions, you know, are they random? Can you figure out when they're coming, the CMEs, since they can be such a big deal? We, just like the astronomer said in the documentary just a minute ago, we don't know yet. I mean, we need to learn more and more about them, whether we can predict when the sun is going to have a coronal mass ejection. We know that they're more likely to happen when we are at a solar maxima. Like right now, since we're just going up, they're not very likely to occur at all. But come 2026, we probably will experience, you know, one or several or many. How do we know when it's going to be a really big one? And they're working on it. This is research that is happening as we speak. And so in the meantime, how do we prepare against solar storms? What can we do? Well, first of all, thankfully, our planet has a magnetic field. So at least that shields us against a lot of the fury of the sun. But the other thing that is nice, so right now we don't know how to predict when a super CME will happen, but we do get to see it 8 minutes after it happens, right? So a CME goes off like the one behind me, no, behind me here, and we see it, the image, right? The light arrives 8 minutes after it happens. But the actual CME, the actual mass, has to travel, and it travels a lot slower than the speed of light. So it comes to us and it takes 2, 3, maybe even 4 days, depending on how fast it is coming. And so, and until it gets to us. So that gives us a warning that allows us to take some measures to prepare for the CME. How do we prepare? Satellites, if they know that they're going to be hit by the CME, they can be shut down because sometimes if the electronics, you know, it's kind of like when there's a thunderstorm, which they don't happen here in Riverside very much. But when there's a thunderstorm, you know, when I was a kid, I grew up in a place where we had thunderstorms all the time. And if there's a lot of thunder, lightning, you want to unplug your electronics, because if you don't have them connected to the grid, you are less likely to get fried. I mean, the electronics are less likely to get fried. So it's something similar what they do with the satellites. They could power them down, wait for the CME to come, and then power them back up. Grids, electric grids, it's something similar. I was reading just before class about how they are trying to come up with capacitors that might be able to trap that charge, you know, as the charge comes to the grid, that goes into the capacitors. And so to keep it from, you know, extending throughout the grid and then bringing everything down. So in my opinion, they're not working fast enough for this. This is a big deal, right? I mean, if we go without electricity for 3 months, it's not just light, right? It's internet, it's and everything depends on internet, right? Your bank accounts and everything. So it would be quite a disaster if this were to happen. So we're getting there. And again, just like it's very important to search for any asteroids that may be coming our way, that and to protect ourselves against them, this is something else that needs to continue. If you ever have, you know, if it ever comes to US citizens voting for, you know, whether we should keep, or US citizens or Japanese citizens, or, you know, there's many, sorry, I didn't mean to sound America centric, but European citizens, you know, they all have satellites. And if we ever have to vote, you know, whether we should continue to have them or not, I recommend that you vote that we continue to fund these projects, because they are very important. And as some of you said, kind of apocalyptic. So, all right. So, oh, one more question. Somebody asked, I forget who, would a coronal mass ejection be harmful to us in any way? And I said, not so much, but no, yeah, I mean, astronauts actually, when there's going to be a coronal mass ejection or a lot of solar wind, they tend not to go out of their spaceships, right? Because I mean, if the sun itself can give you cancer, right? I mean, if just the sunlight, the regular normal sunlight, imagine if in addition to that, you get like all these charged particles coming into your skin. So it could be harmful. I didn't mean to say that it was all safe. The difference, so somebody's asking about the difference between CME and solar storm. CME is the coronal mass ejection itself. Solar storm is when you get a lot of them. So like the difference between a thunder and a thunderstorm, right? Very good. I think I answered all. Why can't we predict CMEs? Because we don't know all the ingredients that go into producing a super CME, right? So we're still learning. That's what keeps us employed, right? I mean, I don't study the sun, but you know, my colleague solar astronomers do. Very good. So this is all I have. Oh my gosh, I ran out of time. All right, this is all I have for the sun. And so I guess next time we will start talking about star formation, and hopefully we'll catch up. We're about half a lecture behind. Maybe I talked too much. So anyways, thank you guys. I will see you on Wednesday and I'll stay behind to answer any questions. So let me stop recording.